Okay, so when we left, we were saying that we're going to divide all waves into two categories based on what they move through. And the first category is mechanical waves. And mechanical waves are all those waves that need matter in order to travel. Okay? And a sound is an example. Sound will not travel through empty space. These waves travel best, as in fastest, through solids. Then next best through liquids, and then gases, and then not at all in empty space. Now this should make sense if you stop and think about what do the molecules inside a solid look like. Inside a solid, the molecules are touching, right? They're side by side. So if one of them begins to vibrate, it's going to be really easy for that one to cause the next one to vibrate and the next one, because they're touching each other. They're like shoulder to shoulder. So if you're in a line shoulder to shoulder with people and you begin to move back and forth, you're going to cause the person beside you to do that and the person beside you, and the vibration is going to quickly pass through the medium. In liquids, it doesn't happen as easily, because in liquids, they're like in solids, right? The molecules are connected to the spot. They can't move. But in liquids, the molecules are like running around. Their feet are on the ground, but they're running around, and so they're more spread out. So if one of them begins to vibrate, it's going to take a little bit longer to pass that vibration through the medium, because they're not touching as well as they are in the solids. And then when you get to a gas, they're jumping and running all over the place, right? They're really spread out, and so it's going to take significantly longer for those vibrations to pass through again. Okay, so fastest in solids, next fastest in liquids, least well in gas, not at all in empty space or a vacuum. Best example of this is sound. When you think about like those old Western shows where the guys would be like out in the middle of nowhere and someone stole their horses and they have no water left, and then they come to a train track. They're like, oh, I wonder if a train's coming. And so what do? They put their ear down on the track. And it's because sound travels best through solids. It will get to them faster through solid than trying to listen for it in the air. You right now could put your head down on the desk or the table where you're working and tap, or before you put your head down, tap on the table. Now put your ear right on the table and tap again. You will hear it much, much louder when your ear is on the table. It travels much better through a solid than it will through gas. Okay, same way as if you're swimming and you go underwater and you clap your hands, you'll hear it better in the liquid, in the water, than you would if you clap them in air. Okay, so that's mechanical waves. So water waves, sound waves, earthquake waves, waves in a rope or a string, all of those are mechanical. Just happened to my pen. Why didn't it write? Okay, need a different pen. Okay, so the second type are electromagnetic waves. Electromagnetic waves travel best through empty space. They do not need a medium. They can travel in some media, but they don't need a medium. Okay, they travel best in a vacuum. And again, by best, we mean fastest in a vacuum. Next best would be gas, then liquid, and least well in solids, and in some solids, not at all. Electromagnetic waves are light. Visible light is an electromagnetic wave. Actually, the whole light spectrum. So X-rays, gamma rays, infrared, UV, all of them are electromagnetic waves. They travel best or fastest through a vacuum, so the sun's light rays that are coming from the sun are traveling through a vacuum when they reach us. When they enter our atmosphere, they slow down a little because now they're traveling through gas. If they hit the water, they're going to slow down more. When they hit a side of a building, they slow down even more and they don't travel through it. Okay? Think of light rays, electromagnetic waves, as like you running in an empty hall, or you running in a hall. If the hall's empty, you can run at your fastest speed. But if there's a few people in the hall, you kind of have to zigzag around them to be able to travel through. So you have to slow down a little, and that would be like in a gas. Maybe when you're running in the hall at school, someone has their class out in the hall, and they're scattered kind of all over the place doing an experiment. Now that's a liquid, so you have to slow down even more. And then a solid would be you trying to run up the main stairs at dismissal time when 1,000 students are coming down. You won't get very far. That would be like light traveling through a solid. Okay? So those are the two types of waves, mechanical and electromagnetic. And actually for electromagnetic waves, they all travel at the same speed in a vacuum. And we'll come back to this, but that speed is 2.9979 times 10 to the 8th meters per second. And you'll hear that number a lot as we go through this unit. Okay? So that's one way of categorizing waves based on what they move through. A second way is based on how they move. How they move. Okay? And there are three here for this one. Whoops, I'm right at the bottom of my page. So okay, so the first one, they're called transverse waves. Trans means across. And so a transverse wave is actually the type of wave you're most used to. It looks like this. Okay, where the equilibrium position, if the wave wasn't traveling through it, the medium would just be here at rest. Each little molecule in this wave is vibrating up and down. Right? Every one of them. The wave itself, though, is going this way. And so transverse waves are where the direction of motion is perpendicular to the direction of vibration. They're cross, trans, like trans-Canada, across Canada. Okay? These are waves, you would see them. Light is a transverse wave. We could make these waves on a rope, or if we were in school, a slinky. A ball game wave is a transverse wave, right? You stand up and down, but the wave travels around the stadium. Okay? That's a transverse wave. A longitudinal wave is the second one in this category. Longitudinal. And these guys, we would draw the molecules like this. And so if there was no wave going through a material, we could say the molecules would all be equally spaced. But now in a longitudinal wave, I do something to cause a vibration, and the molecules are going to vibrate back and forth this way while the wave travels like this. So they're vibrating in the same direction or parallel to the direction of motion. Okay? Examples here would be sound wave or compression waves. Sound is the most common type of longitudinal wave. And then the last one is surface waves. And they are a combination of both. Water wave is a surface wave. And if you're ever to watch something that's floating in the water, it goes over a little and then down and then over and then up. So at some points it's parallel to the direction of motion, and at some points it's perpendicular, like if the wave is traveling this way. So it's a mixture of longitudinal and transverse, where the particles are traveling both parallel and perpendicular. Okay, so we'll come back to waves tomorrow, and we'll get into more